When searching for the optimal hyperparameters of a gradient boosting model for a specific task, we've seen that we can often test hundreds or even thousands of different combinations of hyperparameters and select a set of hyperparameters that lead to the best results on the validation set. We can do this because the training times are typically not that high. However, when we train large deep learning models, such as large language models for processing small molecules or proteins or both, we typically don't have the computational resources to test hundreds or even thousands of different combinations of hyperparameters. So how can we find suitable hyperparameters for our large deep learning models? As I already said, typically we don't have the resources to test many combinations of different hyperparameters, hence we need a clever way of finding suitable hyperparameters. Let's first shortly define what hyperparameters are. Hyperparameters define the settings or configurations that control and define the learning process of a model. And these parameters are not learned from the data during the training process, but instead they have to be set prior to the training process. And examples for important hyperparameters include the learning rate, number of layers, dimension of layers, batch size, or the dropout rate. First, we will look at how we can find a suitable batch size. The most important thing to note about the batch size is that studies have found that the final model performance does not depend on the batch size and that the same final model performance can be achieved with any batch size. Of course, you have to tune other parameters such as the learning rate according to the batch size, but if we do this, we achieve the same performance. As a consequence, the batch size should not be treated as a tunable hyperparameter, but only set once at the beginning. But how do we decide which batch size we should choose? Typically, the ideal batch size is the largest batch size supported by your available computational resources. The reason for that is that larger batch sizes reduce training time. And if you have completely unused resources, then doubling the batch size should also double training speed. But you can simply test the training speed by trying different batch sizes. If you select the batch size such that it gives you the highest training speed, the advantage is of course that you can do faster test runs when searching for good values of the other hyperparameters. As a consequence of this finding that the batch size doesn't really matter for final model performance, we can also conclude that in most cases we don't need gradient accumulation, which is a technique to simulate larger batch sizes than your hardware can support. But it does not provide any training speed advantages, and hence we can also pick the batch size that still fits on your hardware. It is also important to note that many other hyperparameters are sensitive to the batch size. This means if you decide to change the batch size at a later point, maybe because you move to larger computational resources, you need to retune other hyperparameters. In particular, you need to tune again the learning rate and the momentum of the optimizer, but also regularization coefficients. The next important thing is choosing the initial configuration of your model. One of those choices is choosing the optimizer. It is often a good choice to start with a simple optimizer because they give you typically results that are already very close to the optimal results that can be obtained with other optimizers, but they don't require a lot of fine-tuning. Examples for simple optimizers that typically work well are stochastic gradient descent with Nesterov momentum, but where the momentum is kept fixed to standard default value, or the Adam optimizer with fixed epsilon and beta values. This means in those cases you only have to tune the learning rate. Then you have to choose an initial set of hyperparameters and an initial set of configurations for your deep learning model. A good rule is to start with a relatively simple model that leads to reasonable results. This means you should avoid any unnecessary complexities such as too many layers, complex custom activation functions, or overly sophisticated regularization techniques. Starting with a straightforward model architecture helps in understanding the model's behavior and its responses to different hyperparameters. Later, you can systematically increase the complexity of your model if the initial results suggest that this improves or these improvements are needed. This might involve adding more layers, increasing the number of neurons per layer, or integrating more advanced regularization techniques like dropout or batch normalization to combat overfitting. You can also experiment with different activation functions to see if they improve learning dynamics. Assuming that we now have a running model that is providing reasonable results, we now want to select the model architecture and model hyperparameters that lead to good results. So how can we best tune different hyperparameters of our prediction model? The following rules and guidelines that I will present to you are mostly extracted from the tuning playbook that is published on GitHub by members of the Google research team. While the descriptions on the GitHub repository is far more extensive than what I will tell you, so I highly suggest you to read it. The link to this GitHub page is given on the bottom of this slide. As I already initially said, most probably we don't have enough resources to perform a large grid search to search for the best set of hyperparameters. This means we have to find a different way of selecting suitable parameters. One approach is to incrementally add and test features and hyperparameters in multiple rounds of experiments. This means in each round we only try to find the effect of a single feature, or try to find a suitable value for a single feature or hyperparameter instead of adjusting many hyperparameters simultaneously. If we would adjust multiple hyperparameters simultaneously, we may not be able to disentangle the separate effects on the results, and we might not be able to judge how big the effect of adjusting or adding a specific hyperparameter was. On the following slides, we will see how such a round of experiments can look like. For this, we will define three different classes of hyperparameters. Those three classes are scientific, nuisance, and fixed hyperparameters. And to which class a specific hyperparameter belongs depends on the experiments that we are currently performing. We call those hyperparameters whose effect on the model performance we currently test these scientific hyperparameters. For example, we could test how the effect of the number of encoder layers is for the model performance. In this case, the number of hidden layers is our scientific hyperparameter. All hyperparameters that need to be optimized again for fair comparison of different values of the scientific hyperparameter are called the nuisance hyperparameters. For example, we can only fairly compare different numbers of hidden layers if we test each setting with different learning rates, because the optimal learning rate typically depends on the size and depth of the model. And finally, we call those hyperparameters that we keep fixed during this round of experiments the fixed hyperparameters. We decide to keep these hyperparameters fixed either because we believe they don't have an effect on the results for testing the scientific hyperparameters, or because we only have limited computational resources and we decide that the effect of tuning those hyperparameters is not important enough. Ideally, we would make all hyperparameters that are not scientific hyperparameters nuisance parameters, but of course for doing this we typically don't have the required computational resources, and hence we have to make a lot of hyperparameters fixed. We will now look at how such a round of experiments can look like. First, we need to define a clear goal that states what we actually want to test. For example, the effect of an additional feature or the best value of a specific hyperparameter. Here I listed 3 examples for such a goal, or for how such a goal can actually look like. For example, the goal could be trying a new pre-processing technique, understanding the effect of the activation function choice, or finding a good dropout rate. Next, all hyperparameters have to be divided into scientific, nuisance, and fixed hyperparameters. We've seen on the previous slide that scientific parameters are those parameters whose effect we want to test. So if we want to test different dropout rates, then the drop rate is the scientific hyperparameter. Then we have to decide what the nuisance parameters are. If we would simply test different dropout rates while not adjusting other parameters, this would not be a fair comparison, because it could be that Different dropout rates are optimal under different learning rates. So we should make, for example, the learning rate a nuisance parameter, which means we test for each dropout rate different learning rates to make sure that we didn't select a suboptimal dropout rate because the combination with the current learning rate wasn't optimal. And it is indeed usually the case that the learning rate and also other optimizer parameters are set as nuisance hyperparameters because different settings or architectures typically lead to different optimal optimizer and regularization parameters. Then we would have to decide if we want to make additional hyperparameters to nuisance parameters. For example, we could make the number of hidden layers to nuisance parameters because we could expect that the dropout rate depends on the number of layers. But if we are very limited by computational resources, we could also decide to make these to fixed parameters. In this case, our results might not give us the full picture of how we could apply dropout best for this type of model, but since we cannot test the effect of all hyperparameters at each step, we have to make such decisions where we make some parameters that could have an influence to fixed parameters. So finally, we make all hyperparameters that are neither scientific nor nuisance parameters fixed hyperparameters. So far, we have set a goal for what we want to test next and decided which parameters we want to make scientific, nuisance, and fixed. Now we have to design and execute the next round of experiments, which means that we first have to define the search spaces that we want to explore for the scientific parameters and for the nuisance parameters. We now have two options to explore the defined search space. We can either manually define all combinations of parameters that we want to explore, or we could also explore the search space by using a search algorithm to randomly explore different configurations in our defined search space. We always have to make sure that we have made the search spaces large enough and that we have selected suitable upper and lower bounds. If we, for example, see that we got the best results when we were at the border of the search space for one or multiple hyperparameters, we did not select suitable search spaces. For optimal results, we would then have to rerun the experiments with adjusted hyperparameter search spaces. Finally, in the last step, we want to evaluate the results of this round of experiments. If the goal of this round of experiments was to check if adding a feature improves model performance, or if the aim was to decide what the best value for a specific hyperparameter is, we need to evaluate whether a new value or a new feature leads to improved results compared to our baseline approach that we used before. This isn't very obvious even if we see an improvement in validation error compared to our baseline. The reason for that is that if we retrain the same model with the exact same hyperparameters and the same configuration, but with different random seeds, we would get slightly different results. So we have to make sure that our improvements is greater than the random variation between training runs with the same settings. One way of investigating this could be to rerun the best trial that we have found in this round of experiments and see if this configuration is consistently performing better than our previous baseline. If we find that the new configuration is indeed better, we can adopt this configuration and make it our new baseline for the upcoming round of experiments. However, if the improvement is only small and the adjustments would massively increase the complexity of the model, we still might want to decide to stick to our baseline that get slightly worse results but didn't have such a high complexity. We can now summarize how each round of experiments looks like. First, we set a goal. Typically, we want to test whether we should add a certain feature to our model or we want to find a good value for a specific hyperparameter. Based on this goal, we then divide all hyperparameters into scientific, nuisance, and fixed parameters. We then design and execute the experiments of these results, which includes the selection of suitable search spaces for all scientific and nuisance hyperparameters. And finally, we evaluate the results and decide whether or not we adjust our current configuration. When doing many rounds of experiments, we typically start with broader goals, such as whether or not we should include specific features at all, which can be described as an exploration phase, and in the later rounds of experiments, we typically move towards more specific experiments. So, for example, in the initial exploration phase, we could ask questions such as which hyperparameters should we include, for example, dropout and weight decay, or which activation function we should use. And in the later exploitation phase, we can be more concerned with finding good values for specific hyperparameters. For example, finding a good dropout rate or deciding how many hidden layers we should use. Similar as for the batch size, it is recommended to not treat the number of epochs as a hyperparameter. If you have enough computational resources, you can select the same maximum number of epochs that is large enough for all training runs. And large enough means that you can train until the validation error is not improving anymore. During each training run, you can save after each epoch the model and select after training the model that resulted in the lowest validation error. And you can check if you selected the number of epochs not too large by making sure that your best model is not always occurring, for example, in the first 20% of the training epochs, because this would mean that you could lower the number of epochs and save computational resources and training time and still get the same results. On the other hand, you should also make sure that the number of epochs is large enough by making sure that the best model is not typically, for example, among the last 20% of training epochs, because this would indicate that training for longer probably would increase model performance further. In this case, it might be useful to increase the maximum number of epochs. And you can, of course, only do this if you have a lot of computational resources. If you are computationally quite limited, you could also select a much lower number of epochs during the earlier rounds of experiments in the exploration phase, because this might still give you a good idea about what features you should add or should not add to the model.